We'll quickly discuss what we discussed last time. What did we discuss? Yeah. Well, we were specifically talking about we have some data like this. We have some system. We've applied some input. I think we call it A. This is some system. Okay, we don't know what is inside. We don't know the input-output behavior. So we've applied some input, observed some output, and we have this table. Right now, I'm only talking about a single input, single output system. We have some, let's say, M measurements, and we are interested in fitting a linear model, right? So where vi will say is equal to x into ai, but x is our parameter. The general case would be vi will be equal to well, yes, some ai rho multiplied by x. Right? For the ith measurements, these are the set of inputs for the ith measurement, and now it's related to your parameters. Okay, if you express the whole thing, this would be in the form right where both these, what are these two? A and B, those are fixed, and those are your measurements, and this is your unknown system or model parameter. Okay. All right. If this is the setup, how do we find out the parameters x? So this is what we discussed last time, right? What do we do? Well, okay. We specifically started by saying we are dealing with what kind of A? What is the shape of A? Tall, right? And can we really solve this if A is tall? No, we can't. No, it depends. Oh, okay. If it's not, then you cannot solve this. But even if we cannot solve this, we can maybe find an approximation for B uh, in terms of this model if we appropriately choose X. Okay. And how did we say we can go about finding out that approximation? No, we posed it as a problem, no, as an optimization problem. What is optimization problem? Well, there is no X that will give me exactly B, but can I find an X that gives me AX that is as close as possible to B? How would I pose that as an optimization problem? Yeah, right. So, well, if we want AX to be as close as possible to B, then we're saying the difference between these two should be as small as possible. But the difference is a vector. Okay. The, we need to convert this into a scalar to find a minimum, right? So we said we'll take norm. Which norm do we take? Well, let's take the second norm. And the problem was minimize this over all possible Rn is m cross n, where m is given. Okay. And what is the solution to this problem? Yeah, A minus x transpose. Okay. So if this f of x is simply this, And what is the solution to that? There is an analytical solution for this, right? Or x star or x cap, whatever we. Well, it's just this. And what is the condition for this to exist? Right. This has to be null. Right. Then you can solve it like this. Okay. This is the first thing we looked at. And we cannot get B by multiplying A by x star. But what do we get? We get some B star. This is x star. Okay. And what are we doing here? Can we do this? What is the relationship between B star and B? Yes, B star is the orthogonal projection of what? B onto A? No, not A. A is a matrix. You project onto a subspace, right? What is that subspace? Onto. So whenever you see a least squares problem like this, you should immediately think orthogonal projection. Right. And then what did we talk about? Well, I can write here. What did we talk about? Multi-objective. Okay. What is this? Well, we said, what if we don't just have this thing that we want to minimize, but there are a bunch of things we want to minimize for the same set of parameters. We want to minimize this, minimize this. Okay. If we have a whole bunch of stuff that we want to minimize, then how do we deal with this problem? Or one way of dealing with this problem? Yeah. You guys have to review. Yeah. We said, okay, each one of this is a scalar function of x. We'll simply add all of these together and stick some weights to them. Okay. And call this our single scalar function that we want to minimize. We again talk, and beta, rho i's are greater than 0. Okay. We again had a analytical expression for this. What was it? It turns out if each of your uh, terms here that relates the B term to the A term is a linear model, then this whole thing can in fact be expressed as a optimization problem like this with the modified A and modified B. So we said A tilde. So this is equivalent to minimizing right? What is A tilde and V tilde? Root of rho 1 A1, root of rho 2. Same thing. So on and so forth. Okay. And when can we, again, we can say, well, now the optimal solution is, but under what condition? A tilde is full rank. And when is A tilde full rank? In this case, Hey, there are k of them, right? There are k. Yes. If any one of them is full rank, A1 to AK is full rank, then you can show that this is in fact full rank. So that's the only condition. Okay. And then we then talked about the case where we only had two. Talked about this, and then we talked about the role of lambda here, or rho, whatever we've used before. Note that rho 1 is 1, rho is simply rho 2 by rho 2 by rho 1. And what is the role of rho here? Rho is again a positive number. How does the solution to this problem, how is it affected by rho? See, notice now if you find a solution for this, right? X star would be a function of rho 1, rho 2, rho 3, rho k. Depend if you change, see these are from your experiment. Whatever experiment you've done, this is data. BI and AI are data that you cannot change. This is what you have. X is what you're trying to find out. The rows are again under your are knobs that you turn. Okay. So whatever solution you obtain for this combined optimization problem really depends on rho 1 to rho k. So here I should say X star is this, but X star is a function of rho 1, rho 2 to rho k. If you change these, then the value that you get is different because your A tilde and B tilde are now different. And then we talked about this. So how does rho affect? So here, if you find, let's say the optimal solution to this is some X star. The optimal solution is actually a function of rho. How does rho affect the solution to this problem? Oh, what happens when rho is 0? Let's assume A1 and A2 both are full rank. So what will be the solution when rho is 0? It will be the minimization of this problem. Then your X star will simply be, or rho is very large. Then this is equal to, and for values in between, it's something else. It's not necessarily something in between, but it's some other value that kind of tries to balance the cost that you incur here and the balance that you cost and the cost that you incur here depending on the value of it. Okay. And how would you choose this rho if you had it? I mean, a multi-objective problem with just two objectives like this. What is one way of choosing rho? No, not regularization. Well, the choice of rho, you choose rho so that both of them, you're minimizing both of them to an amount that is agreeable for you, right? So if this is J1, then you simply look at this plot, and then you should be able to then make a decision on a row that. So if you simply solve this problem for different values of rho, you'd get a graph like this. And depending on your application, you try and you choose something that gives you low values for both J1 and J2. Okay, all right. After this, what did we talk about after this? After multi-objective, right? What happens when A is not right? What is one possible approach? The regularization approach. Well, if A is not full rank, then we simply convert This is not invertible anymore because A is not full rank. So you change this so that it is full rank. Okay, and this is in fact equivalent to a minimization problem. What is a minimization problem? This type of an expression, you'd get this for an equivalent minimization problem like this. What is that minimization problem? The solution to the optimal solution for this is essentially this. Here, lambda is a positive number. And this is called here it does not matter if A is does not have full rank. This is always invertible if you choose lambda appropriately, so there is no problem. Okay. And then and finally we talked about we're talking about again this, but there is a constraint that I mean we can find the solution to this using this is a constraint optimization problem with equality constraint, so we can use the Lagrange method. And then you will actually end up with a matrix like an expression like this. This will be B, this will be 0, this will be X. Something like this. No, find B like this. If the condition is if AC is invertible, or so not invertible, this is not invertible, it's full rank. Then it turns out this will be invertible, so you can solve for this. Okay, this is where we stopped, right? This is essentially the theory of basic theory of linear least squares. We will look at some applications now as to where we might be able to use this for solving real problems. See, are there any questions about the material? Okay. See, the most popular application is linear regression. That's probably one of the most popular models in statistics. And in linear regression, we're essentially talking about a problem where we're making a bunch of measurements, okay, xi. Output variable. See, these could be, for example, maybe I'm just making this up, blood sugar level, right? We are interested in finding out in building a model to see if we can estimate somebody's blood sugar level based on some other variables that are related to the person. Okay. What are some variables that might be related to the person? Well, okay, let's say age, BMI. Okay, what is? Sure. Well, maybe the amount of exercise they do, and maybe the amount of alcohol they consume, and so on and so forth. Okay? So we might have a bunch of variables, and just call it Y. Uh, Variables that tell us something about the person, and Y is a variable that we are interested in estimating using these variables. Okay. See, we might not. So I'm essentially saying if I'm given xi, I won't use f. Let's say I have some function p that will give me the correspond. Well, if I give all these variables, the measurements of all these variables, we want to be able to compute this person's blood pressure using some model. Okay. So you could ask, okay, why do you want a model like this? Let's say there are 15 variables here, right? And then we are saying, oh, we want to make these 15 measurements to actually predict this variable. Okay, that makes no sense. Where blood sugar level is actually easy to measure. Okay. So you might want to build a model like this, not necessarily because you want this is a variable you cannot estimate and you want to estimate this variable using other measurements. If y was very difficult to measure, right, then it makes sense to build a model like this to say, okay, these are all easy for me to measure, whereas this is very difficult for me to measure. Then it makes sense to have a model like this to be able to compute a difficult variable using variables that are easy to measure. That's one possible uh, reason for building a model like this. Another reason could be when these are all easy to measure, you still build this model because you want to see how changes in a particular variable really impacts uh, this output variable y that you're interested in. So how these variables are related to this might actually be useful, even though my primary purpose is not this model, but to see how are they related to each other. Okay, and often, I mean, of course, the relationship is likely to be very complicated and non-linear, right? But often you would start with a linear model and see how well these variables explain changes in blood sugar level. So what you would end up doing often is to build a model like this, where you say my output variable y is depends on all these variables. Well, and this is really a population level model. Okay, you're going to be collecting all this data across different people in a population, and then you're trying to build a linear model. Okay, linear regression model, and that model usually looks like this. And y is your whatever output variable is, blood sugar level here. Is some beta naught. Beta naught is the average blood sugar level of the population. So if you gave me no information about any of these input variables, and you ask me what is this person's, let's say, average blood sugar level, you'd simply report this number because this is the average blood sugar level for this population. Okay. But let's say if I have age, maybe I can do a little better than this number. I'll say, okay, it's beta 1 times age. Okay. Again, age and blood sugar level might not be linearly related, but this is better than just saying the average value. Okay. Similarly, let's say you give me BMI, that might be related to my Y through some other parameter beta, and so on and so forth. And if you're doing stats, you of course tag on an error. But for us, we will not worry about this because we're not doing a statistical treatment of this. So we will not bother too much about this error term. Right? And this is a fairly good start. Okay, you can introduce other nonlinearities here. Maybe there is a reason for you to believe that the blood glucose level actually increases with the square of your BMI or something like that, right? But as long as y is linear in terms of your these parameters of your model, then you're still fine. Non-linearities are allowed here. The betas have to be linearly related to y. If this is the case, then it's still linear regression. Okay. Yes, we'll come to that. Right. Now, let's say, okay, we want to build a model like this, and then later on we want to look at the betas to say, okay, how are these different variables related to my output variable? And the way you go about this, you have a population. Okay, let's say people who come to CMC, you randomly sample them. Okay, let's say we collect data from 1,000 people. Okay, they all agree to provide us the data, and then they consent to us using their data to build this model. The first thing you do is you'll build a table. Right, this is subject 1, 2, so on and so forth. For each subject, you'd fill in x1, x2, xn, y. So you'd measure all these, let's say 16 variables. Let's say n is 15. So you'd have some values here for one subject, and then similarly you'd fill out this entire table by making these measurements experimentally. Once you have this, then it's relatively easy. The most difficult part is getting the data, at least with models like this. Okay? Well, if you have this, then the blood pressure or blood sugar level for subject 1, see, a note, betas are all constants across the population. These betas are uh, parameters that describe this population in terms of the relationship between these variables and this variable. Okay, what varies from one person to other is y and the x size, right? So for the first person, yi is simply beta naught plus beta 1 plus that person's whatever that variable is, x11, beta 2, x22, and so on and so forth. And then you have n variables here, xn, x1n, this is x12, and similarly you have different subjects that goes up to xym. Can we express this in a matrix notation? Okay, what would be the corresponding matrix notation for this? This is essentially m linear equations, right? So we can express it. So the vector y will be related to this vector beta. Beta is, what is the size of this? And what is the size of this? Sorry? Yeah, this is m cross 1. This is n cross 1. M cross n, okay? It'll be a matrix. M cross n. What will be the elements of this matrix though? Well, so note that this is, well, it's not really n cross 1. This will be okay, and this will be simply what will we have here? 0 then? No. What will be the first element? It'll be 1 because it's just beta naught 1. Yeah, that's all. It'll be x11, x12. Right? Once you have that, then that's it. 1 xm1, xm2, blah. That's it. Right? Once we have this, I mean, obviously m will be larger than n. Okay, you might only have 15 variables here, but you're collecting data from 1,000 people. How would we solve this now? How do we find beta? There, of course, this is a tall system. It's unlikely y is in the column space of x. So there is no exact solution to this. So how would we solve it? So what would be the solution for beta? Sorry? Well, I asked for the solution assuming the problem that we are trying to solve is obvious. See here, there is no beta that will give me that'll give me y exactly. Okay, but I want to find a beta that gets as good a prediction for the blood sugar level as possible using these input variables. Okay, so essentially I'm saying I want to minimize. That's essentially x. Yes, I want to minimize y minus. Sorry. And let's say for now we are going to minimize the squared. And what is the solution to this? We've seen this before. Hey, hold on. See, you should note here the roles are different. This was A, this was B, and this was X before. I've used Y, X, and beta because this is often what people use in stats. Let's assume X is full rank. It's the same thing. So, I mean, again, we talked about a model like this. So if we want to build a model that minimizes this, then we know the standard solution. Okay. Yeah. So M, see, I said we are collecting data from 1000. M is, yeah, definitely M is. Okay. I mean, nothing new. Same. It's just a specific example of an application where solution of a tall system where we're trying to minimize this is used. Okay. So once we do this, then any y I cap, right? The prediction of the blood sugar level for any subject, any particular subject, is given by beta naught star plus tau star x I1. Yes. Right? These are the individual measurements for the subject for the different input variables, right? And these are the parameters that we've identified for this population that relates these variables with this output variable, assuming a linear model like this. Right? So our using the measurements of the input variables for the ith subject, the blood sugar level that we would predict would be this. And this is essentially the best we can do with a model like this and the data that we have. Okay, because it's the solution to this problem. Yes. Yeah. Yes. Here. Yes. Yeah. So you measure the blood pressure or blood sugar level. You measure these individual variables, and then you're trying to build a model that fits, that matches these input variables to the output variable as well as possible using this linear model. There might be another model that is able to predict this better, but our constraint is we are saying we only want to have a linear model. Right. So if you have these measurements, this is how you predict. Okay. What do the betas tell me though? What do the individual betas tell me? So those are the questions, but what do they mean? How do I interpret that number? Okay, weightage, more specific. Sorry. Yes, all of them are essentially the intuition behind it, right? More specifically, beta 1 is essentially the amount by which your output variable will change if this variable changes by 1 unit. Okay? See, if I, let's say the value is xi1, if I increase it by 1 unit, whatever unit this is measured in, then your y cap I would simply be the old y cap I plus beta 1 star. Okay, that's essentially what these things simply tell you. Okay, now coming back to this question of if you had the betas and then I asked you, okay, which of these input variables um, have the strongest correlation to my output variable? What would you say? Rank, is it? Rank of what? I mean, what do you mean by rank? Yes. So essentially, one intuition would be, okay, fine. Whichever beta is the largest, then you'd say that is the most controlling, or that has a higher weightage, or that particular variable has a higher weightage to determining the value yi. But there is one problem with that. Let's say we are measuring mass, right? Or, okay, let's say we are measuring, uh, let's say alcohol. Okay, it doesn't matter. Let's say we are measuring one of those variables. I'm using some unit to measure it. Okay, instead of that unit, I say, okay, I'm not going to measure alcohol in the amount of liters they consume. I'm going to measure the number of tons of or I mean, what is the big unit for volume? Gallon is still small, but still per kilogallon. Okay, amount kilogallons of alcohol they consume. That means I've taken my variable x, whatever x I, and I've divided it by a large number, some k. Okay. Well, the model would essentially remain unaffected. What will happen is that your beta I star will now be. Okay. So the problem with just looking at the largest variable is this. By simply scaling the input variable associated with that parameter, you can simply jack up the coefficient beta I, right? So that is not always the right approach. So one way to address that is you take your variables. One way to address this before you start doing the analysis is you ensure that all your xi's uh, are varying more or less in the same range. For example, if let's say age varies between 30 to 80, okay, and you have BMI varies between, I don't know, 10 to 35, these are these look like more or less they're in the same range. If you had something then that varies from 0 to 10,000, right, or something that varies from 0.01 to 0.1, then you have a problem. Okay, this is huge, right, compared to the other ones. And let's say the insulin level is in the range of hundreds. Let's say uh, it's in the range of hundreds. Uh, then you're the same argument that we were talking about here. See, the betas here would definitely be larger than the betas here, just because the scale of the variable is different, the units you've chosen is different. So one way to address this problem, when you're fitting a model like this, it is you would normalize each of these, right? So that they have, so you take this, you find the minimum and the maximum, and then you'd simply divide it by max minus min, so that everything now varies between, let's say, 0 and 1. Okay, then that would address some of these issues with betas. Okay, that's once you've done that normalization of your data, then you are more or less safe in interpreting larger beta as contributing more towards uh, your output variable. So in this case, now let's say 3 of the betas are much larger than the other betas. Then you say those 3 variables are strongly correlated with your blood sugar level. Okay, so that's one way of, like I said, uh, one goal of a model like this would be to see which variables here are related to this output variable. And one way to do that is make sure you've normalized your data correctly, and then simply looking at the size of the beta tells you which variables are the most important in terms of the relationship between these variables and this variable. Okay. Now, this is okay. That's one way to do this. But if you have a situation where you have, let's say, the input variables, you've got hundreds of variables here. Okay. Then what you'd end up having is again lots of betas for you to deal with. And in terms of, for example, so I said we are interested in the relationship between these variables, right? In terms of us gaining an understanding of relationship between these variables and this output variable, um, it's often important that we have only a handful of input variables that are related to the output variable. So in order to gain a rough understanding of the nature of this problem, right? So if you have thousands of variables here and you've got one output variable that you're trying to connect, and there are lots of betas that you have to deal with, that something like that does not really help us in gaining a better understanding of this problem, right? So one approach there is, what people do is, okay, they say we want to minimize, we want to build a model that minimizes this, but we also want to force the model fit such that the size of the betas that we get is kept relatively low. Okay, that means you're essentially saying, okay, see, if you have more input variables here, right? By adding more and more input variables, you can try and get a better fit. Okay, that is always possible. But getting the best fit is not always the the desired outcome, because we might be fitting this model because we want to understand the relationship between these two and not necessarily to predict this value as well as possible. So if you're talking about relationship between different variables, we want to restrict ourselves to just a handful of variables, uh, a model which says that these four variables have the strongest relationship to this model. Okay. So if that is the case, then fitting a model like this, and this is called as ridge regression. So whenever you come across this term, there it's essentially somebody fitting a linear model like this, but they also have a penalty term or a regularization term, whatever you call it, right? Where they're saying fit a model, a linear model that minimizes this error, but also make sure you don't choose betas that are too large. Okay, because if you choose betas that are too large to reduce this error, then this can be a problem. Okay, see, you could ask, okay, where do, I mean, if all these variables are in fact strongly determine my blood sugar, then of course I cannot force my model to have low betas, because if I have low beta, then this error is going to become huge. It turns out when you have in reality, when you have thousands of variables or hundreds of variables, not all of them are going to have strong relationship to this. If you're measuring hundreds of variables, some of them might be related to each other. For example, it's possible, I mean, my BMI is likely to be related to my exercise, right? Maybe my age is related to my BMI. Maybe the amount of alcohol I consume is related to BMI and all that, right? So there is likely to be correlations between your measurements here. And what that often leads to is, if there are correlations here, it turns out that then the betas that you can choose in this model to get a good fit is kind of, so it turns out this kind of becomes an underdetermined problem, because there are different possible choices for beta that you can use to get a good fit. So essentially I'm saying this could be low rank. Okay, this could have might not be this might not be full, might be full rank, but the uh, two or three, I mean, a few columns might be fairly close to each other, that they're not linearly independent. So when you have a situation like this, then the betas that you might get might have very large values, and they might not make sense at all. Okay, and the reason betas are large is because the measurements that you've made here have correlations among them, and that has led to uh, a, a low conditioning number for this. Okay, uh, which results in a large value for beta. I don't know if you guys have completed the SVD assignment. You have? What is the condition number? Do you remember? I don't know if there was a problem where you have two linear equations like this, x1, x2 equals something, then x2 plus 10.1 x2 equals something. Did you do this? Do you remember? Do you remember what is the problem with, so for example, if this changes from 10.1 to 9.9, what happens to the solution? The slight changes here will lead to large changes in your solution. That's essentially, that can happen if you have correlations among your measurement data. So just relying on beta to go to determine what variable is strongly related to my output variable might not always work, right? So often, so if you introduce an additional penalty term like this, then the minimization problem, well, essentially the algorithm that is solving this problem is going to try and force the betas to be small because you've explicitly said keep the betas low. Okay, that's the idea. And I mean, this again has a standard solution. What is the solution for this? How would we get beta star now? Well, it's the solution itself is not the interesting bit. The interesting bit is that by adding this term and choosing some lambda, you can now force the model to choose the really most important variables uh, that relate to the output variable. Again, the way you choose lambda is you play around with different lambdas and then see which lambda gives you a relatively good, keeps the prediction error relatively low while keeping the betas also small. So this is one approach for keeping your beta small. Okay. Another approach, in fact, okay, if you do this, right, what might end up happening is a few variables might have a relatively large beta here, and if you have lots of unnecessary variables, the rest of them might become very small. They might not become zero, but they might become relatively small, right? But if you're interested in forcing the unnecessary variables to go to zero, right? It turns out you can do that by still saying minimize this. Okay? Instead of adding the two norm, if you simply add, if you say don't minimize the two norm of beta, minimize the first norm. Okay? This is called, so I can't remember what the full form is, but you can look it up. It turns out that if you fit a model like this of course does not have an analytical solution. This you'll have to solve numerically. Okay, and we've in fact not covered this in our optimization because all the optimization functions we've talked about are continuous and differentiable. This is not differentiable because if beta is a scalar, right? This essentially is absolute value of beta. Looks like this. It's not differentiable here. So this we've really not looked at how to solve problems like this. But it turns out that if you, instead of minimizing this, if you minimize this will essentially force a lot of these betas to go to zero, okay? Leaving you with just a few betas that are non-zero, which makes the interpretation of the model a little easier. Yeah, that's something to keep in mind. So that's one important application where this linear least squares comes into picture. See, another area where this might be useful is um, in I'll talk about time series filtering. You can use the same approach for filtering images as well. Okay. Let's say we have some measurements that we made like this. This is what we measured, right? And there is an assignment problem like this. So this will essentially help you there. This is let's say x of n, where This is the time index, and this is your experiment. Let's say starting from n equals 0, we measure this. Let's say n equals m or m minus 1. Maybe I should not have used n, but that's okay. This is okay. Well, there are lots of, we know how to filter this. Any standard LTI filter you should be able to use. It turns out that whatever we've studied in linear least squares, you can use linear least squares to solve this problem as well. Okay. Let's say we are interested in filtering out the fast varying noise in this data. Okay. One approach to do that is you say, okay, I have, let's say this x of n, I represent it as a vector like this. Okay. This is a m cross 1 vector. I want to take this x, and then I want to compute a new vector x cap, m cross 1, such that x and x cap are as close as possible. X cap is my filtered signal. Okay, I can simply pose this as minimize this. Okay, I want to choose some x cap given some x such that this is minimized. If I solve this problem, what would I get? Well, you're free to choose any x cap. What do you think? Well, let's do an example. Let's say the signal has 3 points. This is your x. We want to choose an x cap such that the difference between this vector and this vector is minimized. So what would I choose for x cap? If I solve this problem, what should I get? Sorry? Well, just x. Right? If I choose like the lowest possible value for the norm is 0, if I simply choose x cap, I mean, if the best choice for x cap is x itself, right? So that's not really useful. Okay. This does nothing. Okay. So this is not useful. Okay. But the filtering that we're talking about is we know that, let's say we know this signal does not vary very fast. Okay. That means two, or if this is my current value, that means I know that my adjacent value cannot be very different from my current value. Is that clear? Because let's say I'm trying to, I know that this is a slow varying signal, and these fast variations that I see, that's essentially noise. That's not of interest to me, right? So when I say it's a slow varying signal, I'm saying this value is not very different from its neighboring values. Okay, if I go here, I'm saying the same thing. This value is not very different from these two. This value is not very different from these two, and so on and so forth. So essentially, what I'm saying is the true underlying signal, which I'm calling the filtered signal, the difference between the current point and its two neighboring points is not large. Is the intuition clear? That means if I is the current point, then its difference with I minus 1 plus, uh, sorry, I plus 1. That's the adjacent point. I'm saying this is small, which is equivalent to saying 2 times xi minus xi minus 1 minus xi plus 1 is as small as possible. And this is true for all I, right? That means that it will be, I'm not worried about the edge cases. When I is 0, there is no I x minus 1, but you know what I mean, right? Okay. So if I is 0, so this is x of 0, this is x of 1, there is no x of I minus 1 because my signal started from 0. So I'm not going to bother with that. So I'll simply say I. Okay? We'll have to deal with the edge cases slightly differently. And I want to say that square of this is small because I don't care whether it's positive or negative, but this I know is small. So if I simply tag this along here, when I say minimize this, well, it seems like a reasonable problem. But the question is, can this whole thing be expressed as, if you can, then of course we use the standard pseudo inverse to solve the problem. Okay. It turns out you can, because see this term, the terms are only have constants in front of them. That means you should be able to express this, right? Essentially as minimize x minus x cap, you know. And I should change one thing. It's not that this should be small. See, remember xi's are fixed. That's your data. What I will compute in the filtered signal, I want to keep this term as small as possible, right? So it turns out you can express this as some d of x cap. D is this matrix that essentially will give you these terms. Your goal is to then find this matrix D, and the choice of D is deliberate. This simply means D for derivative, because you're essentially looking at how does my signal change locally. So this is essentially something like a derivative, numerical derivative. Okay, so it turns out now. So of course we'll tag along a lambda. If you now, let's say you've found out D, you've chosen a value for lambda. If you choose lambda equals 0, then you get the signal, original signal. If you choose lambda to be very large, what do you think you will get? Sorry? Hey, hold on, x cap is unknown. So I'm asking you, yeah, okay. What will you, so what does this intuition tell you? If this is to be minimum, then what would be my x cap? Sorry? Yes, what is the lowest possible frequency if lambda is huge? Yes, you're right, 0. So if you keep jacking up lambda, if you keep increasing it, initially it might start giving you a fit like this, right? And as you keep increasing, it might then start doing stuff like this. And then eventually, after a particular point, it'll simply give you this. So the solution, if you keep increasing lambda, the solution to this problem is simply the mean of the signal. Okay? Yeah, so the point of all of this is for you guys to get a feel for how does this work, right? So that's one of them. And you can do the same thing for images as well. If you have, instead of a time domain signal, if you have an image has got various pixels. Say this is an n cross n image. You simply convert this into a vector like this, n square cross 1 vector. Okay, and then the same thing. If this is your current pixel, you'll say that the value of this pixel cannot be different from well, this is my original image, x. I want to get a filtered image, right? Such that the value here cannot be very different from the eight values surrounding that pixel. Okay, so so for example, if this point is here, then the relationship to its neighboring points and maybe a few points back and forth, these would be these you would say the difference between these points and a few other points would be as small as possible. So that's another way of implementing a filter, right? Where now you can think of this lambda as essentially determining your cutoff frequency. If you keep large value of lambda would essentially mean low cutoff frequency, and lambda equals 0 means infinite cutoff frequency, low pass filter with an infinite cutoff frequency, because this whole thing will go through. Okay. Well, when you're doing, if you're, let's say, if you're applying a Gaussian filter, you're not doing this. You're simply convolving this image with a with another small image with a particular kernel. Okay, so that's not exactly this. Okay, here we are using the whole image and saying, give me uh, an approximation of this image with some properties. So x cap is the approximation of my original signals, which has the property that it's the value of the signal and its neighbors are not that different. Okay. All right. The last thing we'll look at is again a very simplistic look at CT reconstruction. Okay. Yeah, let's say we had an image or an object that we were trying to image, and let's say it only had 4 pixels. Okay. And the width of these are, let's say, delta. Okay. Again, I'm going to take a relatively simple example to keep the math simple. We'll assume that the scanner is like this, and it's simply there are 4 scanners like this with detectors here, sources here, and detectors on the other end. There are 2 sources here, 3 here, 2 here, and 3 here. Okay, the 2 sources here will essentially pass X-rays through both of these, and let's assume we can measure the intensities of the X-rays that are coming out. The 3 here will essentially pass 3 rays like this, okay, through the center of the pixel. Similarly here, it will pass 2, and this will again pass 3 rays that will pass through like this. Okay. And what we're trying to reconstruct is the absorption coefficient of this body at these 4 values, at these 4 positions, right? The image has 2 pixels. That means there are, how many unknowns do we have? What we're trying to estimate is this. Rho 1, not R1, R2, R3, R4. Those are your unknowns. And your measurements are essentially what you're measuring here. Okay. So you have 4 unknowns. How many measurements do we have here? Well, here we have 10. Okay. So that's great. We have more measurements, and of course, each of them has some noise. We have more measurements than we have unknowns. We can express it like, and the R's here would sit in your X. Okay. Maybe we know how to solve this. If you have and for some, let's say the geometry of the problem is such that A is full rank. You should be able to now reconstruct this image using this. Okay, this is fine if it's a simple 2 cross uh, 2 image. With just these 4 measurements, you're fine. But what happens if you have n cross n? N. Okay. Let's say the height and width of each pixel is lambda. R1, R2, R3, R4. So we have n square unknowns in this case. And let's say our detectors are like this. There's one detector here, this is at 45 degrees, another one here, another source and a detector like this. Okay, such that for the vertical and the horizontal scan, there are n measurements, such that for the vertical scanner, the n measurements, n X-ray beams that you pass will pass through the n columns. The n horizontal scans will pass through the n rows. And here we will have 2n minus 1 uh, X-ray beams, such that they will pass through like this. Well, I'm not drawing it properly, but exactly like this. The beams essentially pass through the main diagonals and the orthogonal diagonals of each of these pixels. Okay, and similarly from this side. Okay, how many measurements do we have now? We have, let's say n is 100. I mean, n is probably in the thousands now with the systems that we have. Let's say n is 100. We have 10,000 unknowns. And how many we have? I said 100 cross 100, right? Yeah. We only have 598 measurements. This is a problem. What is the problem? What will happen if we try to, let's say this again is Ax equals B. What is the problem here? Let's again assume A is full rank. Well, fat matrix. What is the problem with the fat matrix? A is full rank. Can we solve it? No. Fat matrix, full rank. This is a fat matrix that's full rank. This is, let's say, M cross N. Well, I should not have said N. I've used N here. Say P cross Q. P is less than Q. Full rank. That means there are P columns here that are linearly independent. That means the column space of A is RP. That means you can solve this. But what is the problem? There are infinitely many X's. That means the 598 measurements that you've made could have come from an infinite number of possible image uh, absorption coefficient maps. Okay, there are infinitely many uh, uh, absorption coefficient maps that could have given you these 598 measurements. Okay, so that means we don't know what is inside, essentially. So if you try to solve this, what will be the value of this objective function if for the minimum for the appropriate solution x? So it'll actually be 0, right? Because you can solve this perfectly. Okay, so this is not going to work, right? But what you could do is you say, okay, same approach. The organs inside my body, they're continuous, right? That means I don't have a piece of liver here and then a piece of lung and then a piece of liver after that. Right? If I have a liver, then it's occupying a continuous region of space. That means if this is my liver, the neighboring pixels are also likely to be my liver. If this is my bone or bone of some part of my body, then the neighboring pixels are likely to be that tissue. That means their absorption coefficients are likely to be similar, right? Of course, this fails when you have a boundary, right? Boundary between bone tissue and soft tissue, right? But for the most case, but boundaries are lesser than non-boundaries or continuous regions. So one way to address this problem of infinitely many solutions is to say, okay, the neighboring absorption coefficients cannot be that different. Okay, that is equivalent to saying you're adding some d term, not the same as what we had in the time series. This is one way of dealing with that issue, saying that the absorption coefficients form a continuous map and they don't just, from one pixel value to another, they don't jump that quickly. Okay, so if you do this now, you might be able to get a reasonable set of solutions depending on the value of lambda that you choose. Again, what will happen if you choose lambda to be very large? What is likely to happen? What image are you likely to get? What do you mean by clear? Yes, that's correct. The contrast would be low because it's trying to now fit a model, fit or come up with an image where the neighboring pixels don't change that much, right? Well, in effect, you might not see, it might still choose, it might see, for example, it might still choose an x such that this term is 0, but an x such that the values of x's don't change that much. At least the neighboring values don't change that much, right? So you might get an image that does not have a lot of variations. Okay? So you will have a problem like this in your assignment for you to practice, and then see what happens when you play around with your lambda factor. Okay, all right. That's all I wanted to say. If there are any questions about this, we will discuss now. Otherwise, tomorrow we will do a review. So if there are any questions about the optimization assignment, please bring it up tomorrow because you will have problems like this in the midterm. Or if you have any questions about any of the other assignments or the lecture material that we've covered, uh, we will discuss it tomorrow. Okay, there will be a quiz as well tomorrow. Yes? Yes. Okay. Anything else? Hill optimization. This is not in least squares, linear least squares is not included. Okay, all right. Thank you.